Okay, so by now we know how to decompose a rational function into smaller pieces, and we're at the third step of our partial fraction decomposition integration method, which is we need to integrate the decomposition. Let's take a look at some examples. So from case one, we will have integrals that looks like this. This is when our integral breaks up into distinct linear factors. So when we have a linear factor, the first thing we could do is we could factor out a from our integral. We'll have 1 over x plus 3 dx. And we can make a u substitution here. We let u be equal to the denominator x plus 3. This makes du equal to dx. And I can make my substitution. I'm going to get a times the integral of 1 over u du. As we know, that's going to give you a times natural log of the absolute value of u plus c. And then I just want to make sure I sub back, so I get a times natural log of absolute value of x plus 3 plus c. Okay, so that's an integral we would get from case 1. As I was saying earlier, this comes from case 1. Let's look at the repeated linear factor. So this repeated linear factor, this comes from case 2. Okay, and we're going to use u substitution again to solve this one. So I guess I could first pull out a b. I'd get 1 over quantity x plus 3 squared dx. Just like before, we can let u be equal to x plus 3. This makes du equal to dx. So when I make my substitution, I'm going to get b times the integral of 1 over u squared du. Really, I could write that as in exponential form. So this is b times the integral of u to the negative 2 du. And we know that find the antiderivative, you add 1 to the exponent. So we'll have b times u to the negative 1, and then divide by what you just wrote, which is negative 1 there like this, plus c. So in the end, we're going to get negative b divided by x plus 3 plus some constant c. All right, so that handles the repeated linear factor case. When we look at an irreducible quadratic, irreducible quadratics, these come from case 3. From case 3, okay? And the way that we handle this is, when I look at this integral right here, this almost looks like a arctangent type integral. So the first thing I'll do is I'll factor out the c. So I'll pull out a c. I can also write this as 1 over 9 plus x squared dx, because with addition's commutative, you can write it in any order. The next thing I'll do is I'll factor out a 9 from the denominator. So when I factor out a 9 from the denominator, that forces the 9 to be 1. And then I have x squared over 9 dx, like that. So you can verify that if you multiply the 9 in and distribute properly, you're going to get the original denominator there. Okay. Next step, let me leave my constant in front out there, c over 9. I'm going to write this as 1 over 1 plus x over 3 squared dx. So once I write it like this, I think I definitely want to make another u substitution. So we'll have u equal to x over 3. This makes du equal to 1/3 dx, which makes dx equal to 3 du. So when I make my substitution, I'm going to get really c over 9, get my integral of 1 over 1 plus u squared times 3 du. You can see that the 3, I could factor that out. I could factor this 3 out and cancel it with this 9. And when I do that, I'm going to get a c over 3. And then when I find the antiderivative of 1 over 1 plus u squared, that's just going to be equal to arctangent of u plus c. And I just have to make sure that I change it back to x. So I'm going to get c over 3 arctangent of x over 3 plus c. So let me highlight that guy. So as I said earlier, this integral here comes from case 3. Remember, when you have irreducible quadratic, you usually have some linear term up here. But in this particular case, the x coefficient was 0, so we just have the constant. If you look at this irreducible quadratic, this time the x term is not 0. In this case, there's a 2. So this integral is fundamentally different from this one, even though they both come from case 3. Comes from case 3. Okay. So the way that we handle this is pretty straightforward. We're going to split this into 2. So I'm going to take this integral, I'm going to split it into 2x over x squared plus 9 plus 3 over x squared plus 9 dx, like this. And then I can even split this integral up into 2 integrals. So this will be 2x over x squared plus 9 plus, dx plus, I could pull the 3 out, so I'll put a 3 integral of 1 over x squared plus 9 dx. Okay. Now, this second integral over here, we just did this. We just did this in our previous example, right? That's this integral right here. Okay. So then the real question becomes, how do I handle this first integral? And remember, you always want to look for the easiest solution first. In this case, I could just use u substitution. I could use u substitution even if this wasn't a 2 here, as long as there's any x up there, and the x squared plus 9 on the bottom here, or x squared plus any constant down here, we could use u substitution. So we're going to let u equal to x squared plus 9. This makes du equal to 2x dx. This 2x dx is really right here, 2x dx right there. So after I integrate, after I substitute, I'm going to have the integral of 1 over u du. And that's just equal to natural log the absolute value of u plus some constant c. And let's make that natural log of, we got to sub back, x squared plus 9 plus c. All right. So I'm highlighting this part, even though this is just the solution to the first integral we had over here. And this second one we know how to do that. All right. We have a couple more to look at. When you have the repeated irreducible quadratic, this comes from case 4. So this is case 4, okay? And we're going to do the same thing that we did really in the last one. Always look for the simple solution first. I see a x squared plus 3 on the bottom. I see a single power of x on the top. So I think I should use u substitution again. So let's do it. So why don't we let u equal to x squared plus 3. Then my du is equal to 2x dx, which makes my dx equal to 1 over 2x du. Okay, let's make our substitution. So our integral is going to become the integral of, let's temporarily leave the x there. Let's hope it cancels. When I make my substitution, I get u squared in the denominator. And I'll replace the dx, I get 1 over 2x du like this. And we can see that the x's cancel out, which I need to happen when I do substitution. I want everything in terms of u. So now I pull out the 1/2, and I convert this into exponential form like that. And I know how to use the power rule to integrate u to the -2. I simply add 1 to the exponent, which would make that exponent -1, and divide by what I just wrote, which is -1. Tack on a plus c. Okay. And finally, I am going to sub back. So we're going to get -1/2, 1 over x squared plus 3. Let's put that in parentheses, plus c. Okay, and we'll highlight that as our final answer. This last integral also comes up in case 4. Okay, this one is different from the previous one. How is it different from the previous one? In the previous example, we had an x there. That x allowed us to use u substitution. Here, the coefficient in front of the x part is 0, so it's just a constant term here. You could make it 1 or any constant you like. But without the x term, I can't use the u substitution. So in this particular case, I need to use trig substitution. Okay. So when we look at this function, it doesn't even have the square root. So I guess it's not obvious that you want to use the trig sub. But if you look at the shape of this inside, this is x squared plus some constant. To me, this looks like the classic trig sub involving tangent, right? So if you had something like x squared plus a squared, then the trig sub that you would use would be x equal to a tangent theta. Now, in this particular case, we have x squared plus 2, so this means that our a is actually equal to rad 2. We have to take the square root of that number here. Okay, so let's do that. So we have, we'll let x be equal to rad 2 times tangent of theta. And then we always need to calculate our dx, so our dx is going to be equal to rad 2 times secant squared theta. All right, so let's make our substitution. When we make our substitution, we're going to get the integral of 1 over 2 tangent squared theta plus 2. That denominator is squared. And then we need to replace the dx part with the rad 2 secant squared theta d theta. Okay, so let's simplify this a little bit. The first thing I can do is I could factor out a rad 2 from the top, and from the denominator I could factor out a 2 squared, and then I'll have a tan squared theta plus 1. And on the numerator here, I'm going to have secant squared theta, and then I'll leave the d theta off to the side. All right. So I can now factor this 2 squared, which is 4, outside of my integral because that's a constant. So let me do that. So this will be rad 2 over 4. We still have a secant squared on the top. On the bottom was still squared. I forgot to write that, sorry. And then on the bottom, we're going to have we're going to use our trig identity. So we know that this tan squared plus 1, that's equal to secant squared. So we're going to have secant squared squared. That makes it a secant to the 4th theta d theta. All right. So things are going well. We can keep going here. Obviously, we could simplify. We have 2 powers of secant in the numerator, 4 powers of secant in the denominator. So this integral is going to become rad 2 over 4, the integral of 1 over secant squared theta d theta. We know that secant squared is really 1 over cosine squared. So this integral basically becomes the square root of 2 over 4 times the integral of cosine squared theta d theta. Now, how do we integrate the cosine squared integral? Well, this is when we have to use the half angle formula. So our integral now becomes the rad 2 over 4. We apply the half angle formula, which is 1/2 cosine of, 1 plus cosine 2 theta d theta. We're going to pull out a 1/2 here. This becomes rad 2 over 8, integral of 1 plus cosine 2 theta d theta. Okay. So realize this video is running a little bit long, so let's just cut to the chase here. This will be rad 2 over 8. The antiderivative of 1 is theta. We could do the u substitution in our heads, and we're going to get plus. From the u substitution, you're going to get a 1/2 coming out in front, and then you're going to have sine of 2 theta. Okay, we should put parentheses around this whole thing because that's the antiderivative of the integral. And then we're going to have plus c like this. Okay, so I still need to change back to x. My original integral was in terms of x. Right now, everything's in terms of theta. So what I'm going to do is I'm going to distribute this coefficient out in front to both pieces, and I'm going to use the double angle formula for sine 2 theta. So this becomes rad 2 over 8 theta plus rad 2 over 16 times 2 sine theta cosine theta. All right. So at this point, we have to use our triangle. Let me do the triangle in green here. Put a right angle here. My theta is over here. I know that my tangent theta is equal to x over rad 2. That means that the opposite side is x, the adjacent side is rad 2, and the hypotenuse is going to be the square root of x squared plus 2. Okay, so now we can write our final answer. We're going to have rad 2 over 8 arctangent of x over rad 2. When I distribute that coefficient in front, I've already distributed, that's going to be plus rad 2 over 8. I'm going to have 2 times, and then the sine theta is going to be the opposite over the hypotenuse. So that's going to be x over rad x squared plus 2. And then the cosine is going to be the adjacent over the hypotenuse, which is rad 2 over square root of x squared plus 2. And then we still have a plus c. So this whole thing is our answer. This video turned out to be really long because of this last example. Sorry about that. All right, everybody. Take care.